So I'm going to talk about a numerical scheme to compute parallel transport on manifolds. So why parallel transport? So this is a session on nonlinear statistics, and parallel transport is a useful tool to compare quantities defined at different tangent spaces. So indeed we have a lot, as Xavier mentioned, we have a lot of naturally manifold valued data. It can be shapes, it can be tensors from BCI or diffusion MRIs. And so if we want to have statistical approaches on this kind of data, we are going to need to compare tensors defined at different tangent spaces, and parallel transport is one way to put them into correspondence. And it's already being used in several approaches, like horizontal component analysis, for example, or to bring deformation fields in a common reference frame. Now the existing methods to compute a parallel transport are quite expensive unless you have specific features on the manifold you're considering. So if we come back to the definition, so if gamma is a curve, transporting a vector along gamma is amounts to solving an ordinary differential equation. And if you have a system of coordinates, this equation becomes writes like this in terms of the Christoffel symbol. I mean, it's the most standard way to write it. But the problem with this is that you have to compute the Christoffel symbol. So if you want to integrate the equation, you need to access the value of the symbols at a lot of points on the geodesic, on the curve, along the curve on which you are transporting. And there are d cubed symbols if d is the dimension of the manifold. So in general, this will not be tractable. So another approach that was extracted from the theoretical physics literature consists in using the Shields ladder, which gives you a way to approximate the transport along a curve by repeated computations of Riemannian logarithms. So this works well, but you need to compute Riemannian logarithm, and once again, this is usually an expensive operation. In the applications I'll show, it amounts to performing a registration between shapes or images, which is a very costly operation, on which you don't even have control on the approximation error you make. So another solution was suggested by Laurent Younes in 2008. So he noticed that it's something that's known in differential geometry, that if you have, so here gamma is going to be a geodesic, and we have some W vector that we want to along gamma. What we can notice is that the Jacobi field generated by W here from gamma, which is the differential of the family of geodesics when you have when you go at distance h with a varying initial condition in the W direction. So this family of geodesic. This J that you obtain here is actually a close approximation, a second order approximation of the parallel transport of W along the geodesic. So this is this equation here. So once you have this, you actually know that since you have a second order approximation on a small distance h, if you discretize the interval definition of the geodesic, you can accumulate an error and have a linear error in the end. So the question we answered is, how do you precisely do this in the most cost-efficient way, and with theoretical guarantees on the convergence, even when you have to make several approximations at each computation. So here's the setting to compute the transport. So you start with some W to transport at some time t, and you have some point of the geodesic gamma, and what we're going to do is simultaneously compute the geodesic and the transport of W along the geodesic. So this amounts to discretizing this, basically. There are 4 steps. The first one is to go from tangent space to cotangent space, to transport W from the tangent space to cotangent space, because the geodesic equations writes well in the cotangent space with the Hamiltonian formulation. Once you have this, you compute 3 geodesics at distance h with 3 different initial conditions. One is your geodesic, the one along which you're transporting, and the 2 others are with an initial condition perturbed in the W direction. So the initial velocity for this one is going to be gamma dot of t plus W of t plus h W of t. And then you compute the Jacobi field here by numerical differentiation between the coordinates of the 3 geodesics that you have. Okay, so now that this is said, there could be a couple of variations. So this is the most efficient way in terms of complexity to reach a given accuracy. But there could be several variations. For instance, you can show that it would be enough to compute a single perturbed geodesic and not the one here to have convergence of the numerical scheme. And also there is actually, so yeah, this is not, actually I said that the initial condition for this geodesic would be gamma dot of t plus hw of t. And you could have wondered if this would be hw of t or h squared w of t or the square root of h, and it turns out that the best answer is to perturb in the w direction with the same order of magnitude as your integration step. And I also mentioned that to integrate the geodesic equation, you use the Hamiltonian formulations. And why is that? It's because if you want to use the natural expression for the geodesic equation, you have to compute the Christoffel symbols again, and you have to face the same curse of dimensionality that we are trying to avoid. Yeah, and as a small detail, it's enough to use a second order integration step to compute this geodesic, the geodesic points here. Okay, and with this setting, we could prove that, including all the different approximations that you have to make, because you compute, at each step you have some error on your geodesic point, some error on your current approximation of the vector you're transporting, and so on. Even with these errors, you still recover a linear convergence with the size of the integration step, with mild hypothesis being a positive injectivity radius and under a coordinate system, of course. So we implemented this on the sphere to compare the output of the numerical scheme with the ground truth, and we do recover a linear behavior. And we could investigate some of the variations that I detailed, being using a single perturbed geodesic or a higher order Runge-Kutta scheme. And the differences are not very important, less important than in the next case I'm going to present. Okay, so I'm going to show one application of this scheme on a high-dimensional manifold. So I'm going to recall a few things about the LDDMM framework that Alain Trouvé presented this morning. So in our formulation of this framework, we fix a set of control points in the ambient space. So our goal is to parameterize diffeomorphisms acting on shapes that live in a R2, R3, or Rn in general. So to do that, we set a set of control points on the ambient space. We attach momenta to them, and we prescribe a dynamic on the set of control points and momenta that is minimizing in some sense. So here are those are the control points, those are the momenta carried at the control points, and to get a vector field, you convolve the set of momenta at the control points with a Gaussian kernel, for example. This gives you a vector field, and with the time dynamic that you prescribe for the points and the momenta, you actually get a time-varying vector field here. And when you follow the flow of this vector field, you get a diffeomorphism of the ambient space. So you follow the flow between some time 0 and 2 and time 1, and you get a diffeomorphism of the ambient space. So why is this useful? It's useful because it gives you a way to compare shapes through the action of diffeomorphisms on them. And in our case, what we did is, so we're interested in disease progressions, and we saw that we have some reference progression of a subject who has, let's say, Alzheimer's disease in our case, and we wanted to transport this progression onto a new subject for which we only have one observation. One way to do this is to perform a registration between some point on the reference geodesic that you know and the single new observation that you have, and to parallel transport the description of the registration. So the registration is going to be a diffeomorphism ultimately. You transport the description of this diffeomorphism along the reference trajectory, and from each point you can shoot and have a new observation, a new shape, which would be your prediction in this case. So to fix the ideas, here is how it looks. So on the top row you have a geodesic progression of a subject. So it's a person waving his or left arm, it depends. And we wanted to transport this progression onto a new subject for which we only had this observation. With the method I described previously, this is what we get. And we do get something which actually what you would like to see. So the movement has been captured, the movement of the arm, it has been translated to the person on the bottom row, while at the same time preserving the particular shape of this person. So that's what we wanted to do, and it's actually an illustration of why parallel transport is a good tool. Is because here the isometric part, the isometric property of the transport gave you some satisfying properties on the deformation, which results on the target shape. And so the goal of this would be to apply to Alzheimer's disease patients, and we did that. And when we did that, we evaluated empirical method error of the method I just proposed to check the behavior in very high dimension. So this is a plot of the empirical error in dimension 3000, so with 1,000 control points in R3. And we do recover the same linear behavior here, at least with the empirical error. But we noted that if you use a single geodesic, as I mentioned, so a single geodesic, as I mentioned, it gives you a guarantee of convergence. But if you use a single one, then you have an error which is much larger than if you use two geodesics. So ultimately, the most cost-efficient method is to use two geodesics. Okay, so here's the takeaway message from my presentation. We proposed a numerical scheme to compute the parallel transport, which extended some work by Laurent Younes, and we did prove that there was convergence of the scheme, and the only things you need to compute the parallel transport is access to the metric on your manifold and the inverse of the metric, so nothing more. That's all. Thank you.
Questions?
So I just have a question. So you need to have access to the metric and to its inverse. And so what happens if the metric or its inverse is ill-conditioned?
So I don't see why this would be a problem, actually.
So if you have a metric as a positive definite matrix, you want to have access to its inverse. But if you are
right.
in
So actually
really high dimensions, the inverse will be... Sometimes it happens.
Yeah, you're right. But there is some step in which I need to solve a linear equation, basically to obtain the description in the cotangent space of the W vector, and I couldn't do that if the metric is not invertible. So it would probably fail.
Okay, thank you. I have just a question. I have the impression at the end that you are doing the parallel transport not on for the metric for the shape, but for the metric for the control point, no?
Yeah, that's right. We actually transport the deformation itself and not the shapes themselves. So we could, maybe there would be an equivalent formulation of the parallel transport we make with the metric inherited from the diffeomorphism in the shape space, but that's not what we did. We did the transport in the diffeomorphism space.
Yeah, okay. Thank you.
What are the advantages of this method over other methods of this kind?
Okay, so maybe I wasn't very clear. So the other methods, there are two other methods. Shields ladder, which is extremely hard to compute in most cases because you need logarithms, Riemannian logarithms. And the other one would be to integrate the standard ODE description of the parallel transport. And to do that, you require the Christoffel symbols. But there are d-cubed Christoffel symbols, so as the dimension of the manifold gets high, you cannot compute them anymore in a computationally satisfying way.
So, but for your method, don't you need to know the curvature tensor, and that's a lot of functions to compute also?
We don't need the curvature tensor. We need the metric and its inverse, and the gradient of its inverse, as described in the Hamiltonian equation of the geodesic. So no curvature tensor.
Is there any way to generalize it to curves that are not geodesic?
So, sorry?
Is there any way to generalize it to curves that are not geodesic?
So you would have first to generalize the notion of parallel transport in this setting, and I'm not really familiar with that. Maybe there's one, but
yeah, you can parallel transport along any curve.
Oh yeah, right. Oh yeah, no, sorry. I thought you said on nonlinear data that doesn't have a Riemannian structure. Okay, yeah. No, actually I tried, and the approximation with the Jacobi field does not work if the curve is not a geodesic. So it wouldn't work. Yeah, that's a requirement for the method.
Okay. So more questions? Let's thank Maxime again.